SE203 Exercise Physiology. Force control. Muscle force output is characterized by constant inherent fluctuations. Fluctuations influence the capacity to achieve a desired force and production, and intended movement trajectory. These fluctuations are exacerbated by perturbation and have significant implications for task performance. Force control variability serves as a measure of realizing task goals. The higher the variability means poorer, inconsistent performance. Lower variability could mean successful performance. Fluctuations can be quantified according to the magnitude or deviation from a fixed point, or the temporal structure or complexity/randomness. Force control and contraction intensity. Magnitude of variability increases in proportion to force exerted. Differences in magnitude of variability in different muscles. Greater variability in more distal muscles. So the further it is from the anchor point, the more you might see something. Increase in motor unit recruitment and discharge rate as well. Force control. Ability to control submaximal isometric force is predictive of performance during dynamic activities. Muscle force coefficient of variation significantly correlated with manual dexterity like walking and balance. Loss of force control is more significant than loss of strength during early aging. Something that can influence force control. This could be the motor unit recruitment, the activation of motor units comprising a motor neuron and muscle fibers. It innervates and is a fundamental aspect of force control. The nervous system recruits motor units based on the required force. Another factor, motor unit firing rate, the frequency at which motor units are activated, influences the force generated. Higher firing rates result in stronger muscle contractions. Muscle spindles and Golgi tendon organs. These are proprioceptors that provide feedback about the muscle length and tension, contributing to the regulation of force during muscle contractions. Another factor, brain regions. Areas of the brain, such as primary motor cortex and supplementary motor area, play crucial roles in planning and executing movements, including force control. Another factor is sensory-motor integration. The central nervous system integrates sensory information, like proprioception and visual feedback, to modulate muscle activity for precise force control. Another factor is muscle fiber type. Fast-twitch and slow-twitch muscle fibers have different force generation capacity. The composition of muscle fibers in a particular muscle affect its force control. Something else that can affect this is the cross-sectional area of a muscle. So a larger muscle have greater force production capacity. The cross-sectional area of a muscle influences its strength. Muscle length tension relationship. Optimal force production occurs within a specific range of muscle length changes. Changes in muscle length affect force control. Biomechanics. The mechanical aspects of joints, including leverage and joint angles, impact force control. Joint mechanics influence the efficiency of force transmission. Proprioception. Feedback from proprioceptors, like muscle spindles and the Golgi tendons organs, help adjust force during movements and maintain stability. Visual feedback. The visual system contributes to force control by providing real-time information about the environment, aiding in motor planning and adjustments. Precision requirements. The level of precision required for a specific task influences force control. fine motor tasks demand more precise force adjustments. The complexity of a task affects force control strategies as well. Simple and complex tasks may engage different neural and muscular mechanisms. Muscular fatigue. Prolonged or intense muscle activity can lead to fatigue, impacting force control. Fatigue alters motor unit recruitment and firing rates. Skill acquisition. Force control improves with skill acquisition through practice and training. Skilled individuals often exhibit more precise force control. Age-related changes. Age can affect force control due to changes in muscle mass, neuromuscular coordination, and sensory feedback. Neurological disorders. Conditions affecting the nervous system, such as Parkinson's, can impact force control. Force control and force balance. The ability to regulate and coordinate muscle forces plays a fundamental role in maintaining postural stability and achieving balance. Here are some key points to consider in the relationship between force control and balance. Number 1. Muscle force in postural stability. Anticipatory adjustments. Muscles generate force anticipatorily to counteract expected perturbations, contributing to the maintenance of balance. Continuous adjustments, ongoing adjustments in muscle force are necessary to counteract gravity, ground reaction forces, and external disturbances to maintain an upright posture. Number 2. Neuromuscular coordination. Sensory motor integration. The nervous system integrates sensory information, including proprioception, vision, and vestibular input, to coordinate muscle activation for effective force control and balance. Feedback mechanisms. Continuous feedback from sensory receptors informs the nervous system about postural changes, leading to adaptive adjustments in muscle forces to preserve balance. Number 3. Role of core muscles. Core stability. The muscles of the core, including those in the abdomen and lower back, play a pivotal role in providing stability to the trunk and pelvis, influencing overall balance. Dynamic control. Core muscles are dynamically engaged to counteract forces during movements, contributing to dynamic stability and preventing excessive body sway. Number 4. Joint contributions. Ankle strategy. Muscles around the ankle, such as the calf muscles, are crucial for ankle strategy, a common mechanism used to control balance by adjusting forces at the ankle joint. Hip and knee control. Muscles around the hip and knee joints contribute to the control of the body's center of mass, influencing balance during various activities. Postural sway with the neuromuscular system making subtle force adjustments to counteract perturbations. Number 5. Postural sway and force adjustments. Center of pressure, postural sway, measured by the movement of the center of pressure, reflects the dynamic adjustments in muscle forces to maintain balance. Force variability. Variability in muscle force is observed during functional movements and balance. Number 6. Gait and balance. Effective force control is essential during walking and gait, where muscles generate appropriate forces to propel the body forward while maintaining balance. Dynamic activities, engaging in dynamic activities such as sports and other functional movements, requires precise force control to ensure stability and prevent falls. Number 7. Age-related changes. Muscle weakness. Age-related decline in muscle strength can impact the ability to generate sufficient force for balance control, leading to increased fall risk. Sensory changes, like changes in sensory systems with age, can affect the integration of sensory information, influencing the precision of force adjustments for balance. Force control and training. Training influences force control by affecting the motor unit recruitment. Training induces changes in motor unit recruitment patterns, allowing the nervous system to efficiently activate the necessary motor units for a specific force requirement. Increased motor unit synchronization. Regular training improves the synchronization of motor unit firing, enhancing the precision and coordination of force production. Resistance training promotes the development of muscle strength. Endurance exercises improve the ability to sustain force over extended periods, enhancing overall force control during prolonged activity. Joint position sense. Training enhances proprioception, the ability to sense the position of joints and muscles. Improved joint position sense contributes to better control of force and movement. Kinesthetic awareness training activates that focus on body awareness, such as yoga or balance exercises, enhance kinesthetic awareness, leading to improved force control during various movements. Sport-specific drills. Athletes engage in sport-specific training to improve force control within the context of their particular sport. This includes drills and exercises that mimic the demands of the sport. Fine-tuning techniques. Skill-based training, such as technique-focused weightlifting or precise movements in sports like gymnastics, refines force control by fine-tuning the execution of specific techniques. Core strength exercises targeting core strength and stability, such as planks or stability ball exercises, contribute to better force control, particularly in activities requiring balance. Proprioceptive challenges. Balance exercises that create proprioceptive challenges, like standing on one leg or using unstable surfaces, enhance the ability to control forces in dynamically changing conditions. Real-time feedback. Biofeedback devices and technology provide real-time feedback on force output. This immediate feedback allows individuals to adjust and optimize their force control during training. Wearable sensors. Wearable sensors and technology, when incorporated into training, offer insights into force control metrics. Analyzing this data allows for targeted adjustments to training programs. Gradual intensity increase. Progressive overload, a principle of gradually increasing training intensity, challenges the neuromuscular system to adapt to higher force demands over time. Adaptation to load. Training programs that incorporate progressive overload prepare the body to adapt to increasing loads, resulting in improved force control at higher intensity. Gradual load introduction. Introduction in rehabilitation settings, force control is often addressed by introducing controlled and progressive loads to injured tissues. This gradual approach supports recovery and helps rebuild the strength and coordination. Functional movement integration. Rehabilitation programs focus on integrating force control into functional movements relevant to daily activities or specific sports. Force control and training. Variety in training, engaging in diverse training activities known as cross-training, exposes the body to different force control requirements. This diversity enhances adaptability and improves overall force control abilities. Transferability of skills. Skills developed in one type of training, such as resistance training, can transfer to improved force control in other activities, such as endurance exercises or sport-specific drills. Muscle memory. Consistent and repetitive practice of specific movements establishes muscle memory, optimizing force control by making movements more automatic and precise. Skill refinement. Regular and focused practice refines force control skills, contributing to improved efficiency and effectiveness in executing various movements.